Hello all, in this lesson we're going to be studying saturation states, and you're going to need your reference table because we are going to be doing work on table F and on table G. So get your reference table out, I will be asking you questions about that. And in your second page for classwork, please copy down this particular bookwork with these questions. We'll work on those in class tomorrow. And under that, copy down this aim. How can we use graphs and tables to analyze solubility? And then just below that, copy down these do now questions, which we will answer in class tomorrow. Okay, saturation states. Saturated means that a solution or a solvent is holding as much solute as it can hold. So this means that unsaturated would be basically not that, or that the solvent is holding less than the maximum amount of solute. Supersaturated, you may be thinking, is sort of ridiculous, because if saturated means that you're holding the maximum amount, then what could supersaturated possibly mean? Well, if you're thinking it's crazy, you do have a point, because supersaturated is not a permanent state for a solution. It is a temporary, volatile, unstable state where a solvent is holding more solute than it should be able to hold under typical conditions. So what does this look like? Watch this video to see a supersaturated solution in action.
All right, so we have a supersaturated solution. There's more that can normally be dissolved in there at room temperature. It's very unstable. One way to get it to come out of its supersaturated state is just by vibrating it. Sometimes when I set it on the desk, that's enough for it to come out of its supersaturated state. Or the coolest way is by adding a seed crystal. So seed crystals of sodium acetate will allow those ions that are in their supersaturated state to recognize the crystal structure of these sodium acetate crystals, and they'll be attracted to it. And as that seed crystal gets bigger, more will be attracted to it. And as that gets bigger, more will be attracted to it, and exponentially gets larger until it goes back to its saturated state. Let me show you. Just a couple crystals. And if you zoom in, you might be able to see that sort of suspended in the middle of the solution there. And then those at the front of the room in just a moment will be able to see that begin to grow. Can you all see that? So now, when that crystal finishes growing, what type of solution will I have again? So it's gone from supersaturated back to its... Well, let me pick this up and just hold it at an angle for you. And you guys can see that there's much of the solution here. This part of it's completely saturated, isn't it? And you can see the large crystal that we've made at the bottom. It looks almost like a solid chunk of ice, doesn't it? Now also, when you feel the bottom of this flask, it feels quite warm. And we'll talk about why that's so in just a sec.
I hope you liked that video. I'll try to do this demonstration for you live as well, if we have the ingredients. But I would point out, I thought it was great that he mentioned at the end that after that extra solute had fallen out of the solution and recrystallized, it left behind some liquid that was actually just regular saturated. So it, I think, highlights that supersaturated solutions are unstable, but saturated solutions are stable. So the supersaturated solution just wants to become stable, like so many other things in the universe. So let's put this into context. We'll sort of go from ground level to a higher level. Take a look at this example question. You're making a solution. You're starting out with 100 grams of pure water. The solute you choose dissolves in water at a rate of 40 grams of solute per 100 grams of water. So if I have 100 grams of water and it can only hold 40, then just keep that in your back pocket. Describe the saturation state of the solution after each addition of solute below. So if I had 30 grams of solute, you probably understand that it's under 40, which is our maximum amount. So that means that we have an unsaturated solution. Remember that I can hold up to 40, so let's add another 10. And if I do that, the solution would be saturated. It's holding as much as it can. But here's the tricky one. If I add another 10 grams of solute, what state would the solution be in? Would it be supersaturated or would it be saturated? While I definitely understand an argument for either case, I think that the best answer here is, of course, saturated. The reason for that is that I never actually said that the solute that I added in the third step dissolved. All I said was that you added it. I never said that it dissolved. So I don't think we should assume that the solute that I added dissolves because this supersaturated state is such a rare state that only happens with specific substances. So without saying any specific details, I think it's safest to say that you still have a saturated solution, but you have 10 grams of undissolved solute sitting on the bottom. All right, you're going to need table F now, because table F is going to allow us to determine if a given ionic compound is soluble in water. Now our answers are going to come out basically as yes and no. They're not going to give us how much will dissolve in water, just that if it is possible at all. And the way you use table F is actually by looking at the negative ion first. The negative ion is the second listed element in a compound's name, so I'm highlighting them here. So the first thing you look for on table F is to, in the example of the first one anyway, you're going to look up nitrate first, and you're going to see where you find it on table F. So I'm on table F, and I'm looking for nitrate, and I see it right here. It's under the list that's generally referred to as soluble. So that means that I know that nitrate compounds are generally soluble, but I look to see if there are any exceptions to this rule, and I can see that there are not. That means that ammonium nitrate is soluble. Continuing for sodium acetate, I'm going to first look for acetate, and I see acetates here under the soluble list. I look for the exceptions to see if sodium is one, and I find none, so sodium acetate is soluble. When I continue to look for lead 2 chloride, I'm going to look for chlorides in the list. Now, I'm scanning the list, I don't see chloride anywhere, but you may remember this trick from when we would use molecular modeling sets. Chloride is an example of a halide element. It's a group 17 element. So if I can find halide on the list, then I'm good to go. Oh, there it is. I see halides here. So that means that halides, like chloride, are soluble generally. But if they're combined with elements like silver 1, lead 2, or dimercury 1, then they would not be soluble because they would be an exception to the soluble list. So here, the halide is bonded to lead 2, which is an exception. So this would not be soluble. In fact, we would call it insoluble. Let's try this one again for sodium chloride. Chloride is a halide, and when I look at the exceptions down here, I don't see sodium listed. So that means that sodium chloride is soluble, a fact you probably already knew. For calcium carbonate, of course, I'm going to look for carbonate. I see it here under the insoluble list, which means that generally carbonate compounds will be insoluble. But let's see if calcium is an exception. When I see the exceptions here, I can read the exceptions would be combined with group 1 ions. Calcium is not a group 1 ion, it's in group 2. So I haven't found an exception yet. So combined with group 1 ions or ammonium. All right, so calcium is neither one of those things. So I'm going to go with the general rule for carbonates, which is that calcium carbonate is insoluble. Last one, let's look up phosphates. I see phosphate here under the insoluble list, generally. But I wonder if ammonium is an exception. So when I read through, I can see that phosphates will be insoluble unless combined with group 1 ions. Ammonium is not a group 1 ion, it's a polyatomic ion. But there's ammonium listed here, so that means that ammonium is an exception to the insoluble rule, which would mean soluble. So there's another much more difficult way to use table F, which is to predict whether or not a precipitate will form when two substances combine, or when they're mixed. Remember that double replacement reactions between two ionic compounds occur if one or both of the products is insoluble in water. Let's highlight that. And make sure that that's in your notes, because this is a very important idea. It'll save you some heartache on the reagents. All right, let's use table F and an example. Silver nitrate and sodium chromate solutions are mixed together. Will a precipitate form? If so, what's the name of the precipitate? So to solve this, let's write a word equation for a double replacement reaction between silver nitrate and sodium chromate. At the moment, this is hypothetical. As you can see, what I've done here is I've done a double replacement reaction between the sodium and the silver, a very hypothetical one. I don't know if this would actually even occur just based on what I see here, but I switched the silvers and the sodiums. So instead of having silver nitrate on the right, I have sodium nitrate, and instead of having sodium chromate on the right, I have silver chromate. But we can use table F to determine whether or not this is just hypothetical or whether it's real. What we need to do is check the solubilities of the hypothetical products on table F, so these products. So everybody use table F right now and check to see if a nitrate with a sodium ion would be soluble, and check to see if chromate with a silver ion would be soluble. So I just checked table F, and I could tell that all nitrates are soluble with no exceptions. So sodium nitrate is soluble. And I also just checked out the chromates. Chromates are generally insoluble. There were some exceptions listed. Silver was not one of them. So that means that silver chromate is in fact insoluble. And it's this finding that sodium chromate or silver chromate is insoluble, which is going to influence the question, or the answer to the question, about whether or not this is just a hypothetical equation or whether it really would occur. Remember that double replacement reactions always produce an insoluble product, or double replacement reactions always produce a precipitate. This is what a precipitate would be. This is the insoluble product. So if a precipitate is forming, then we can safely assume that the double replacement reaction is not hypothetical, it's real. All right, and just to fill in the information here at the end, which we've already talked about. And will a precipitate form? Yes, and its identity is silver chromate. Table G. All right, open your reference tables to Table G. So Table G gives us a much better idea of how soluble certain substances will be at given temperatures. And one of the things that's really key for understanding this graph very well is to understand what these lines actually represent. And these lines are really just a series of data points. So basically, you can imagine that a scientist was studying potassium nitrate, and he was trying to dissolve it in a certain amount of water, in this case 100 grams of water. And he did it at varying temperatures, 0, 10, 20, 30, all the way up to 100. And he would basically see how much potassium nitrate he could get to dissolve at 10 Celsius, at 20 Celsius, at 30, at 40. And he would find that he could get certain amounts to dissolve. Like at 10, he could get that much. At 20, he could get that much. At 30, this much. And all the scientists would have to do at that point is connect these data points with a smooth curve. And if you do that over and over again for many different substances, you get a series of curves, which you can refer to as Table G. So Table G is really just a series of curves that represent the saturated solution for that compound in 100 grams of water, that's important, at a specific temperature. So we can answer some amazingly specific questions about specific compounds at specific temperatures and specific masses of water just using this one table. It's a little intimidating at first, so let's do some examples. Which of the listed compounds would be considered gas? Well, up here at the beginning, I point out that Table G shows saturation points versus temperature for common substances, and as you can see, most curves increase with increasing temperature. You probably remember from a previous lesson that the only substances who would increase their solubility as temperature increase would be substances that are solid at STP. The gases, however, would decrease their solubility with increasing temperature. So I'm generally talking about the curves like ammonia, sulfur dioxide, and hydrochloric acid. Since those three decrease as temperature increases, it's safe to assume that they're gas. Let's try another question. At 50 degrees Celsius, how much potassium nitrate is required to saturate 100 grams of water? So we know that these lines are saturation curves, so we know that by looking up data that we'll be able to figure out how much is required to saturate. And we know that 100 grams is how much of water we have, so everything seems normal. Let's just go to the place where 50 degrees Celsius intersects potassium nitrate's line. So as I home in on this, I'm going to go to 50 degrees Celsius first, and I'm going to move up until I can touch potassium nitrate. It is here. So this is a data point. I need to read on the y-axis the value. So I go all the way over here, and I'm getting something around 85. Because this is sort of a fine-tuned question, but the chart itself doesn't have a lot of fine-tuned demarcations, you may find that you're off by 1 or 2 grams for any of these answers. The regents will understand that, and they'll give the graders some leeway with a few points of mass to go on either side. So in any case, what's the saturation state of a solution of 70 grams of potassium nitrate in 100 grams of water at 50 Celsius? So in this case, I want to go to 70 grams and then first, and then move over until I hit potassium nitrate. So here's 70 grams. I'm going to move over until I hit potassium nitrate, and it's here. So this is the data point that we're referring to. And we want to know what's the saturation state at 50 degrees Celsius. So here's the thing. At 50 degrees Celsius, which is down here, the potassium nitrate could actually hold up to 85, which we had said in the previous state. But we see in this question that it's only holding 70. So 70 grams at 50 degrees Celsius is a little bit less than it could actually hold. In fact, it's 15 grams less. So we're going to go ahead and call this unsaturated. For the next question, it asks, what's the saturation state of a solution of 84 grams of potassium nitrate in 100 grams of water at 50 Celsius? So it's very similar to this question up here. The only difference is that instead of it being 84, I had said 85 up here, which means that what I was really going for was 84 grams, so I'm going to change that now. And we're going to base our answer on this. So if we have 84 grams in 100 grams of water at 50 Celsius, then that means we have a saturated solution. But if I were to cool the substance down and see what would happen to that solute as it were cooled to 40, think about this. If I cool it to 40, it would only really be able to hold about 65 grams. That's what I'm seeing on this axis. So I'll write that down. But it used to hold 84 grams. So this means that after cooling, 19 grams of the potassium nitrate will fall out of the solution and become a precipitate. So recognizing saturation states. How can we tell the difference between saturated, unsaturated, and supersaturated solutions in real life? The first thing you need to realize is that if there is any undissolved solute at the bottom of the flask, it is always saturated. The reason for this is the definition for saturation. Saturated means that a solvent is holding the maximum amount of solute that it could possibly hold. So, if you see some undissolved solute on the bottom, then think, what is the solution above that solute doing? It must be holding all that it can hold. Otherwise, this solute on the bottom would be dissolving. So if it's not dissolving and it's just sitting there, then you know for a fact that the solution above that solute is a saturated solution. Let's imagine in the next scenario that the solution does not contain any undissolved solute. Well, in that case, it's much harder to tell what's happening, because if there's no undissolved solute, you could imagine that it perhaps could be an unsaturated solution. Additionally, perhaps it's saturated. Perhaps it's holding exactly the amount that it can hold, and there's nothing on the bottom. And furthermore, it could, in fact, also be supersaturated, because from the eye, you can't tell if a solution is supersaturated or not. What you should do to figure this out is to drop a seed crystal in, just like the guy from the video earlier in the lesson did. If you drop a seed crystal in, you're going to get one of three outcomes. If the crystal does not dissolve, but instead falls to the bottom of the solution, but no other special events occur, then you can say that the solution was saturated before you dropped in the seed crystal. But if the crystal does dissolve, then obviously the solution used to be unsaturated. And this last one you already know. If you drop the crystal in and it causes massive recrystallization, then you know that the solution was supersaturated. But do you remember the answer to the next question? After the above situation occurs, the solution is now saturated. And with that, we have finally reached the pair-up. Copy down these questions without solving them. We'll do them in class tomorrow. And follow them up with these summary questions. We'll do these in class tomorrow as well. Thanks for watching and have a great night.